Welcome back to the deep dive. Today, we are opening up a file that, well, honestly, it might trigger a little bit of PTSD for anyone who's ever tried to design a psychology experiment,
Or a linguistic study, yeah.
or really any science where you have to
Yeah.
deal with just the sheer messiness of people.
It really is the fundamental headache of behavioral science. It's the thing that keeps researchers up at night.
We're talking about noise, but not, just random static like a blurry photo. We are talking about a very specific kind of nightmare where your noise is coming from two completely different directions at once.
It's threatening to just swallow your result.
Exactly. It's like on one side you have the people taking your test and people are just unpredictable.
Right. They get tired, they get bored, they have different backgrounds, different skill levels. It's chaos.
That's source number one, the human element. But then on the other side, you have the actual stuff you're testing them with. The words, the sentences, the images.
And those aren't all the same either.
Not at all. Some words are just harder to read. Some images are more memorable. So you've got variation from the subjects and variation from the items.
So the big question, the million-dollar question, is how do you find the signal, the truth in all of that noise when it's coming from both directions?
For a long time, the answer was messy. But today, we're digging into a solution that has pretty much rewritten the rule book. We are exploring mixed effects modeling.
And we're specifically unpacking Chapter 7 of the book, Mixed Effects Modeling, analyzing fixed and random effects with R.
Which is really the definitive guide, isn't it?
It is. It marks the moment the field sort of grew up. It's about moving away from these old clunky statistical hacks and embracing a method that actually respects the complexity of the data.
And just to set the stakes here, because I think people hear statistics and they just think it's about getting a p-value for a paper.
Right.
If you get this wrong, if you use the old ways, you aren't just getting slightly worse results. You might be finding facts that are completely false.
Yeah. That is the reality. You might publish something that's true for the, say, 20 people in your lab, but it fails completely for the rest of the human race. You're just finding patterns in the noise.
What a terrifying thought. So let's build this up from the ground up. The title is Fixed and Random Effects. In normal English, random just means unexpected.
But in statistics, these terms are incredibly precise.
So help us out. What's the difference?
This distinction is everything. If you get this, you get the whole concept. So let's start with fixed effects. Think of a fixed effect as something repeatable, something the researcher controls.
Okay. The source used in the audio experiment example.
Right. Imagine you want to know if adding white noise to a recording makes it harder to understand. So you have two conditions, clear audio and noisy audio.
So I have a noise button on my machine. I can press it or not press it.
Exactly. And that button is repeatable. If I go to a lab in Tokyo tomorrow, I can recreate clear and noisy perfectly. The definition of noise doesn't change. That's a fixed effect.
Got it. It's part of the design.
Yeah.
But then we have to bring people into the lab.
And that's where the chaos starts. You have your subjects, let's call one Bob, and you have the specific words Bob is listening to. These are random effects.
Why random? Bob is a real person. He's sitting right there.
Bob is real, but he's not repeatable. You can't photocopy Bob. He is just one random sample from the giant population of all humans.
Yeah.
If you ran the experiment again next week, you wouldn't get Bob, you'd get Alice. And Alice is different. Maybe she hears better. Maybe she's a musician. Maybe she just didn't sleep well.
So random just means sampled from a larger pool.
Precisely. And the same thing for the words. If your test uses the word apple, that word is just a random sample from the dictionary. Next time you might pick banana.
So here's the trap. If you treat Bob or apple like they are fixed facts, like they represent all people or all words, your math is going to be way off.
It becomes useless for generalization. The source is so blunt about this. If you treat random effects as fixed, you're just being incredibly overconfident. You might prove that Bob struggles with the word apple. Great.
You've written a biography of Bob?
You've written a biography of Bob. You haven't proved that humans struggle with words. You've confused a historical event with a scientific law.
And mixed models are the bridge that lets you do both.
That's it. They let us look for the fixed effects, the science, while simultaneously modeling all the messy random effects.
Now, before these models, specifically this R package on May 4 that the book is all about, what were people doing? There was a kind of dark age of stats, wasn't there?
Oh, absolutely. The traditional trap, or what we call the language as fixed effect fallacy.
That sounds bad.
It was a hack.
Yeah.
Researchers knew that people and words were both problems, but their math, mostly ANOVAN, it couldn't handle both sources of noise at once.
So what do?
They cheated. They would run one analysis where they averaged everything for each person. They called that the F1 analysis. That handles the person noise, but ignores the word noise.
Okay.
Then they'd go back, reshuffle the data, and run a totally separate analysis averaging over the words. That's the F2 analysis.
Suggest. Hope they both showed the same thing.
That was literally the gold standard. You'd look at both and go, well, F1 is significant, F2 is significant, so I guess we're good. It was clumsy, it was super conservative too, so you often missed real effects.
The source brings up this quantitative dataset to show why this fails.
Yes, quantitative. It's a fake dataset, but it's designed to be a stress test. It's a crossed design, which means every subject sees every item.
Which sounds good, right? More data.
It's the ideal design, but the old math just chokes on it, especially if you have missing data. Say Bob gets tired and skips the last 10 questions.
Which happens all the time.
All the time. In the old ANOVA world, that missing data just breaks the machine. You'd end up throwing out good data just to make the spreadsheet square so the math would work.
That's crazy.
Yeah.
Deleting real science just to make a calculator happy.
That's exactly what was happening. And this is where the mixed model, using ELM4, just changes the whole game. It handles those crossed random effects natively. It looks at the subject and the item at the same time.
And it doesn't care if Bob skipped a question.
It doesn't care. It just uses whatever data you have. The simulations in the source show mixed models have way better power, meaning you're more likely to find a real effect, but crucially, without increasing your risk of false positives.
Okay, so it's just a better tool, but I want to get to the part that really blew my mind. It's not just about a better p-value. It's about seeing things the old models just could not see.
Yes.
We have to talk about random intercepts and random slopes.
This is the game changer. This is where we go from, a cartoon sketch of the data to a high-definition 3D model.
Okay, so let's visualize this. We're plotting data on a graph. Let's start with the random intercept. What is that?
Okay, imagine a graph where the vertical axis is your reaction time. A random intercept is basically giving every single subject their own starting line.
Right, because some people are just faster than others.
Exactly. We know Bob is naturally a bit slow. Maybe he's just cautious. Alice is naturally fast. Maybe she's a gamer. If you force them both to start at the same average point, you're kind of lying about the data from the start.
You are. The model might think the task is hard, when really it's just that Bob is slow.
Right. The mixed model says, no, the task is fine. Let's just adjust for Bob being Bob. It gives Bob a higher intercept, a higher starting line, and Alice a lower one. It strips away that personal variation.
It levels the playing field so you can see the real effect.
Perfectly put.
Okay, that makes total sense. But then, random slopes. This is the one that feels like magic.
It's not magic, it's just nuance. A random intercept says people have different starting points. A random slope says people react differently to the experiment itself.
Okay.
The relationship between your variable and the outcome might be different for different people.
The source uses the lexic data for this, the lexical decision task.
Right. Simple setup. Is this a word or not? Press a button. They were looking at the effect of trial. Basically, do you get faster or slower as the test goes on?
Okay, so my gut says there are two possibilities. One, I get tired. I get bored, my eyes glaze over, I get slower, fatigue.
Correct.
But two, I get in the zone, I figure out the task, I get warmed up, I get faster. Practice.
Exactly. Two opposite forces. Now imagine half your subjects get tired, their reaction times go up, and the other half learn and get faster, their times go down.
If you use a traditional model that just averages everyone,
What do you see?
the up cancels the down. You get a flat line.
You get a flat line, and you publish a paper saying time on task has no effect.
Which is a complete lie. It had a huge effect, just a different effect for different people.
Precisely. The mixed model with random slopes allows every subject to have their own slope. It saw that subject A was getting tired and subject B was getting faster. It captured both realities at the same time.
That is wild. It lets the model say the effect is real, but which way it goes depends on who you are.
And that's the danger of the old ways. You lose the real story in the aggregate mush.
Okay, there's one more concept in here that sounds a little fishy at first. Shrinkage. And the terrible acronym that comes with it. BLUPs.
Best linear unbiased predictors. BLUPs. It sounds like a mistake, but it's brilliant.
Okay, so unpack shrinkage, because that sounds like we're manipulating the data, we're fudging the numbers.
It's actually the exact opposite. It's a safety mechanism against being fooled by pure luck. Imagine you're testing reaction times. You have one subject, S4.
Yeah.
S4 only answers 3 questions before the computer crashes. But by sheer chance, they happen to answer those 3 questions insanely fast. like superhuman fast.
So the raw data says S4 is the flash.
Right. A traditional model looks at that and says, fact, S4 is the fastest human alive. It takes that extreme data at face value. That's called overfitting.
And if you tested S4 again tomorrow, they'd probably be normal, and your model would look silly.
Totally. So what the mixed model does is it uses the information from everybody else. It looks at the whole group and says, hey, the average human reaction time is 500 milliseconds. S4 is at 100. That is wildly unlikely based on what we know about people.
So it pulls them back.
It shrinks their estimate toward the group mean. It essentially says, I believe S4 is fast, but I don't believe they are that fast. It realizes an extreme score on very little data is probably just luck.
It's dealing with regression to the mean before it even happens.
That's it. It makes the model slightly less accurate for this one data set, but it makes it much, much better at predicting what would happen in the real world. It prevents you from being fooled by outliers.
It's like a built-in skepticism filter.
That is a perfect way to put it.
I love that. Okay, we've covered the theory. But the source really comes alive for the case studies, these puzzles that only mixed models could solve. Let's start with the Dutch neologisms.
This is a classic, wait, that can't be right moment. It's a priming study. They showed people made up words ending in reheid, like labbeheid.
Okay, and the standard assumption in psychology is that priming helps. If I see a word once, I should be faster the second time.
Facilitation, yeah, your brain is warmed up. But when they ran the simple analysis, they found the opposite. Priming was inhibitory. People were slower the second time.
Which makes no sense.
None. So they used the power of the mixed model to add another predictor. They looked at what happened the first time the subject saw the word.
And what did that show?
Well, because these were nonsense words, a lot of people hesitated the first time. They thought, wait, labbeheid? Is that a real word? No, I don't think so. They rejected it.
Ah, I see where this is going. So when they see it again...
Their brain has to do a complete U-turn. Wait a second, I saw this before. I thought it wasn't a word, but here it is again. Maybe it is a word.
That confusion caused the delay.
So it wasn't that priming failed, it's that the person's decision history mattered. Exactly. By modeling that specific history for each subject, did they accept or reject it, the mixed model found the true effect. For the people who accepted the word the first time, priming worked perfectly. They were faster.
You could never find that by just averaging the group.
Impossible. You needed the model to disentangle the confusion from the priming.
Okay, case study 2. The 8-year-olds learning to read.
This was analyzing reading speeds in kids. The key variable was word length. Obviously, longer words are harder.
Sure, cat is easier than unconstitutional.
But the mixed model used random slopes for word length, and it showed something really subtle. Not all kids struggle with length in the same way. Some kids had a steep slope, every extra letter really slowed them down. Others had a shallow slope. They handled length pretty well.
And it also found that ceiling effect, which I thought was fascinating.
Yes. The model saw that the relationship wasn't just a straight line going up forever. It found that by the time a word gets to be about 9 letters long, the kids are pretty much responding as slowly as they physically can.
They've maxed out.
They've hit the ceiling. A 20-letter word isn't twice as hard as a 10-letter word because the kid is already at maximum difficulty. A traditional model would have missed that curve completely.
That's amazing. It captures the biological limit of the child.
And that brings us to the third case, which moves away from reaction times into corpus linguistics, just counting words.
This was the Dutch versus Flemish newspapers.
Yes. They were comparing how often words ending in leek, which is like the English appear in the Netherlands versus Flanders. Now, counting things is mathematically tricky.
Why? A count is a count.
Well, you can't have negative words. You can't use a word -5 times. The normal bell curve doesn't really work. So they used a generalized linear mixed model, or GLMM, with a Poisson distribution.
Okay, that sounds fancy.
It's just the right tool for counting things. But what's cool is the visual they made. They plotted those BLUPs, the shrunk estimates, for each word on a map.
And what did the map show?
It separated the national preference from just general word frequency. So it found that a word like mogelijk, which means possible, is used way more in Flanders. And a word like landelijk or national is used more in the Netherlands.
But isn't that just saying some words are more common than others?
It's more subtle. It separates the fact that mogelijk is a common word everywhere from the fact that it gets a specific Flemish bonus. It disentangles the word effect from the country effect.
So it's not just that the Flemish use more adverbs. It's that they specifically like these adverbs.
Exactly. You can see the cultural preference hiding in the frequency lists.
So let's zoom out. We've gone from white noise to Dutch newspapers. For the listener, what's the big takeaway here?
I think it comes down to respect. Respect for your data. The old methods, they treat the differences between people or between words as an annoyance. As noise you have to average away to see the truth.
But the mixed model says the noise is part of the truth.
Precisely. The fact that Bob is different from Alice isn't an error, it's reality. And by modeling that reality, you get results that are just more robust, more replicable. You stop fooling yourself.
It's about being honest about how complex the world actually is.
It really is. It's moving from a cartoon sketch of behavior to a high-definition photograph. And once you see the photograph, you realize the cartoon was missing half the story.
And that leads me to a final thought I want to leave everyone with. We just talked about how these models showed that some established facts, like that inhibitory priming, were actually statistical illusions.
That's the scary part.
So if the old models have been failing to account for how individual people react differently to things, ignoring those random slopes, for decades,
You have to wonder, don't you?
how many facts in our textbooks right now are just artifacts of bad math? How many theories are built on averages that don't actually describe anyone? It might be time to open up the archives and reanalyze everything.
I think you're right. It might just be time for a spring cleaning of the scientific record.
A huge thank you for breaking this all down. Mixed models are clearly not just for the math geeks, they're for anyone who wants to get closer to the truth. Thanks for listening to The Deep Dive.
My pleasure.
We'll see you next time.